Definitely not finishing up slides. That would be very irresponsible, wouldn't it?
Just let me know when you're finished.
Now, anytime, are there people still popping in?
One has just disappeared.
One, so we have negative balance on, well,
I think that tends to be connection issues. They'll probably come back.
they better. What did I do? Oh, yeah. Okay.
What's this button? Right. Hello. Right. Good morning, everyone. Welcome to session 29 of BGA24. This session is going to be covering Smudgeplot by Camille Yaron. Please take it away.
Hi, everyone. How is, so, uh, are you here? Would you mind turning on the cameras for a second? Hey, friendly faces. I'm glad the genome scope was not all that bad. Yeah, multiple friendly faces. It's good to see you all. It's nice to meet you. Um, at the beginning, I would like to ask who of you have used Smudgeplot before?
I haven't yet, but keen to.
So no one. So I was trying to hype people on. Yay! How was it for you? We have one user in the chat. It was great. Ah, it's okay. I can read. It's a skill I acquired early in childhood. Good. So good users. So I was trying to hype people up on doing something that will definitely backfire, which is trying to do a live release of the new version of Smashbot here with you. And so I was just wondering what will be the proportion of people here that will be for the tech update and just seeing the cutting edge, or what will be the people, fraction of people that would like to just learn how to exploit it. So if it's the later, that it's good. There's absolutely no disappointment of waiting for you. If you're in the first category, the I got to say I was perhaps slightly over ambitious with what we will manage, and the code is not just production ready, so we will not be hitting uh, publish new version button today. However, I thought that if I would just show you the old code and the old tutorial, there would be no point in doing this in first place. So I will show you some of the bleeding edge code, and you will actually be working with it. You need to be mindful that you need to things can break, but I think it's also a bit exciting, and you always feel free to just switch to older versions that have years of stable users, and they are very well documented cases, widely used in widely, not widely, I guess both widely and wildly used on all sorts of genomes out there. Right, so yeah, just scroll at the beginning and share my screen. So I will have a few sections. I would actually appreciate if you would manage to keep the camera on, because I actually do look at people's faces just to get a sense whether they understand things. Um, I'll first go through what the Smudgeplot actually is, what it's trying to do, and what it's trying not to do. Then we will just go through the practicalities of how to operate the software. And in the end, I have some development notes, and we can discuss a bit the inference, and maybe I can encourage you to participate. It's an open source project. By now, we have about 15 contributors over the last 5 years. Usually, it's like one line, so I would hope to engage more, but it's all I'm saying is contributions are welcome. And we do have like a very nice, friendly community. There are like lots of friends I have, like Smudgeplot friends. Right, okay, to the chase. When we sequence genomes, it's a bit like harvesting hay, because what we really truly want to know is how the individual stems look like, and what we really get is the pile of pieces of a hay. It's the And the idea of doing just assembly is that well, this is a reconstructed one stem, but it's a very complicated, complex process that is very hard to appreciate, hard to understand, and how to actually have a sanity for, or like the sense of how sane was the assembly that we made. Now, all sorts of problems in assembling genomes. If you have a region that is too heterozygous, it sometimes get assembled separately. If you have a region that is too similar to each other, then it can collapse. And imagine that now that you would be mapping back reads and calling variants, and you would be trying to guess what's the ploidy. And looking at different regions, you would get different answers, right? The purple ones would have one, the red one would have four, and the black ones would have two. So it's sort of fundamentally it's a complicated process. Let's appreciate it. It's just challenging. So having something that allows us to do something else, something orthogonal, is extremely helpful. And that's the idea of genome profiling or the schema analysis. And that is that instead of trying to assemble systems, we just try to guess something about it. So in I always stick to the plant analogy for too long. So I will just leave it there. Guessing something about hey. And the trick is actually ridiculously simple. It's just that you will be cutting every single sequence to all the possible subsequences. So if you have a read, you will just take the first two case base, second to case plus one base, etc. And the K is the kmer in K, it's the K, the kmer, and it's the length of the substring you'll be chopping a read into. And that's sort of what you will be doing. The point of that is that you will be then comparing the whole sequences to each other. And if we think about the whole entirety of a sequence and wonder about whether it correctly represents the template that you have sequenced, for reads, although the sequencing rate is relatively low, it's actually a relatively small fraction because they're long, and just longer read you have, higher chances that you will actually have an error. Well, if you chop that read into all possible subsequences of a relatively short length, like I don't know, 21 or 31, a single nucleotide error will be propagated only on to 31 kmers, while every other kmer that came from the read will actually represent the correct genomic template. So by looking at a proportion of correct kmers, you will be looking at much higher proportion in proportion of correct reads. So you're improving the signal to the noise ratio. And it also gives you the ability to separate these genomic kmers from these error kmers, which is extremely handy because then you can have a lot easier data set to work with. And the magic is that you can do perfect matching. So instead of just wondering what is or what is not well alignable sequence, you just simply say how many times I've seen something. And and then you can just wrote the number down. So for this kmer, we've seen it in total 28 times in the whole read set. For this kmer, it was 31, etc. And you write down for every single kmer you've observed in the data set. And what will happen is that you will see a bunch of sequencing errors with low frequencies. So this is just plotting this histogram. Well, histogram of these numbers. Okay. You will see a coverage peak that will correspond to the bulk of the genome. You might see there's some small, like more repetitive bits on the right. You might see heterozygous sites on the left that would be halfway between the homozygous peak and the errors. Well, at zero. This is called Genome Scope. There was a tutorial about that a week ago. If you would like to dig deeper into that, I would refer you to that tutorial. This already, gosh, it's 7 years since the first release of the first Genome Scope. So there is lots of materials out there. And the method is just simply guessing genome size, error rates, heterozygous repetitiveness, just using what we call Kmer spectra, which is histogram of the numbers of observations of individual kmers. here are links to those individual resources. And one I would like to highlight here is this Genome Scope online environment where you can just simply drag and drop KMA histograms and it will just give you the plot, and it's sort of that simple. And I would say Smudgeplot is a tool that is very useful, but it should not be done without Genome Scope. Like they are coupled, and so I'm stopping by Genome Scope just because it's the step number one. You should always start with Genome Scope, and looking at Smudgeplot is the step two. But I will not go into detail about that. So we were talking about how these individual peaks correspond to individual ploidies within the genome. That when we had two peaks, the later one was the homozygous gamers, and the first one was the heterozygous gamers. But what if we see something like this? And it becomes non-trivial to imagine of what's actually going on, whether this is diploid with duplications or triploid or what's actually going on. And for that, we developed Smudgeplot. For exactly, actually, these are meladogene ruder nematodes, and because we were very confused about their ploidies, we developed the tool. That's actually really how it all started. And it's that is based on an idea of being able to find from the Kmer bulk all the Kmers that differ by a single nucleotide. We call them hetemers because what we hope for is that most of these schemas will represent heterozygous pairs. And it does make sense because usually, even though genomes are repetitive, the amount of repetitiveness and amount of duplications within the genome is actually vastly overwhelmed by the amount of differences you have between haplotypes. So you imagine that if you will be searching for all the sequences that are different just by one nucleotide, it usually you will get the signal that corresponds to your ploidy because it will show your heterozygous. So just to clarify a bit, that we will search for all the Kmer pairs that differ by one nucleotide, but also form a unique Kmer pair. So this one would work. This one doesn't have a pair, and this one is not unique. So you see that this one is one nucleotide apart from this one, and this one is the one nucleotide apart from that one. So that would make like a clique of three, right? So because they don't fulfill the uniqueness criteria, we just say we don't care. We don't want to deal with that stuff. And this will actually get rid of lots of the repetitive bits we are not all that interested in looking at anyway. And if you take all those schema pairs and then you just do simple transformation of just summing their coverages and looking at the relative coverage of the one that has smaller coverage, which we always try to label B. They will project on individual places in the 2D plane. So if you plot these two axes between against each other, you will see that the pairs with different ploidies will just show up in the different spaces within this space. And this is what we call the smudges. So there will be a smudge underneath AB, a smudge underneath AAB, a smudge underneath all of those labels. And the intensity of that smudge will tell you something about your genome, or the relative intensities. So in the example I showed you, if you do this transformation, it shows you this kind of smudge plot. So you see that the most intense one is AAB, which would suggest that this is probably a triplet genome. So yeah, that explained the wonder we had. That's pretty neat. The other way how to think about this schema pairs is that it's actually telling you how these peaks correspond to each other. So if you have A, B smudge, it means that both A and B are in one n copy number, which means that both of them will be within this first peak. If it's AAB, then A is in two copies, so it means that it's in this peak, and B is in one in the peak, so it's in this one. Okay. So the intensities of those individual smudges will give you an idea about the strength of the relationships of the individual peaks within genome scope. I will just wait for 10 seconds for you to absorb that because it's a sort of one of the fundamental bits people quite often miss. And I think it's very important. Just appreciate for a moment that if you know for the two members within a pair, the respective ploidies, you know in which peaks they are within genome space. Okay? Good. You see that on the left. Now that's a different rudor nematode. The histogram doesn't look all that different, but if you look at the smudge plot, it just gives you a new brighter smudge to this AAB. So this is a case of a tetraploid. I guess what I didn't tell you is that these rudor nematodes are the very wicked creatures, and they have different ploidies for different chromosomes. So that's why they actually have some chromosomes in diploid state, some in triploid, and some in tetraploid state. So that is weird degenerated apomictic nematode. But that's why it gives you sort of like a very strong, beautiful signal. But we always enjoyed of how Smudgeplot is able to visualize that. It was always the highlight of Smudgeplot performance. So it scales. So the more perceptive of you might notice that the visualization have changed, so much more sleek and polished. Oh my gosh! I wish I would have access to that code. Guess what? But the point here is, it scales to practically any ploidy. I was thinking that this separation or this requirement for uniqueness will cause that the probability of seeing two different variants within 8 haplotypes must be non-trivial. So I was worried that we will just lose too much of the signal, right? Because if we said that we always want only k-mers that differ by 1. So if we have two different variants within the 8 haplotypes, we would discard it as non-unique pair, right? Everybody with me? But it's not the case. Actually, vast majority of genetic variation that exists in any population, that's fundamental population genetics, is rare. Which means that even if you have octoploid, if it's not too heterozygous, means that if there are not that many markers, you will always see things in the right ploidies. So, okay, what happens if you don't have a signal to look at? So this is a male hymenopteron. That means that obviously there is nothing that possibly can be heterozygous because they are monoploid. Well, they're actually haploid. I usually try to distinguish between the two because haploid means reduced. So for tetraploid species, haploid is diploid. Monoploid is the word we usually seek, like a meaning each chromosome is there once. But in this case, it's both because males are actually reduced. So what are we looking at? Would anybody have a guess of what this AD and AAB are? You can also just read it out of the slide. I don't know why I do this. They're just simply paralleles. You just happen to have things within genomes that are similar and are located in different locations, right? And because the signal of paralleles is much, much weaker than the signal of heterozygous sites, you see a lot more of the background noise. You see lots of K-mer pairs that are not represented at all. Those are all the white spots. And you see all this sea of noise down here, which are just pairing of all sorts of strange sequencing errors with genomic K-mers. And then you can tell because if you look at the position of this smudge and this smudge, you can actually guess what's the one-end coverage. This would be 109. So and you see that this is 100. So all this is approximately one genomic k-mer and one error at different ratios. Well, especially those are genomic with error, and these ones will be errors with errors. Okay. But I guess I would like you to appreciate that if you have a haploid organism, you will always see a smudges anyway. You should not think that you have a diploid organism just because you see a smudge. There's no universe in which you can see no smudge at all. It's a relative measure. It's like a in situ hybridization. It depends on how you turn on the dial. Even weak signals you can see and exaggerate. It will always light up something if you have sufficient coverage. And actually, the same applies for completely homozygous diploids. This is a different wasp. This is a female wasp. But this is of a species that does what it's called gamete duplication, which is this wicked parthenogenetic mode where they just double the same copy of chromosomes. So it means that they also have absolutely zero heterozygous sites. And but the funny bit is that here you should not label it as AB because the ploidy of that species is still two, although the two will be always and always identical. So the two and so you always see just paralogs. That's still true, but the bottom paralog will be AABB, right? Because it's a diploid species. It has everything in two copies, but we know for sure that A and B needs to be paralogs. So AA is the one homozygous site and BB is the other homozygous site. And if you would do exactly the same with a male, you would just have to relabel them to have one lower ploidy. And just for the record, it's nearly impossible to get this inference right. You cannot just simply assume that Smudgeplot before you label these peaks right. If you there's no signal that you could possibly use. This is fundamentally, if there's no heterozygosity, there's absolutely nothing you can anchor your 1n coverage on. So what you have to do is to look at the genome scope and compare it with the Smudgeplot and just see that the estimate of 1n coverage actually matches. One, well, 33.9, 34, close enough. That's good. And here it will be, I will do a small drive-by. Genome scope, beautiful tool, but it will just fit your model because it assumes something about sequencing coverage and about how genomes are constructed, right? And here we're sequencing hymenopterans. They have a wicked GC content. This is all Illumina data. What do you expect? I would expect bias. I would expect that it would not be a very nice negative binomial distribution as genome scope expects. What I would expect is that the left shoulder will be elevated, and it is. Like this is very clearly skewed distribution to the left. So when you actually fit their diploid model, they will still find you 0.3 or estimates you 0.3 heterozygous sites, which is absolutely nonsense. This species is entirely homozygous. I can guarantee you that. So just keep in mind, these are models. They are not meant to be religious. They are meant to be, if any of the assumptions of the model are not met with your data, of course the numbers that you will be getting will be somewhat misleading. If you're a biologist, that's your role to make sense out of it. Gosh, so another example of where Smudgeplot can go wrong. I think I vastly will be presenting things that will go wrong. But most of the things I will give you to work with will be those that hopefully will work. I think. Let's see. This diploid strawberry, although is diploid and is heterozygous, it's actually quite often selfing. And yeah, funny fact, not all strawberries are octoploid. They also happen to have quite a lot of quite recent duplications. And if you just do Smudgeplot on the data with K17, what you will actually see is that the AABB is much more dominant smudge than AB. And it is just simply because there is very little of the heterozygous signal and there is quite lots of the duplication signal. It's just very unfortunate. And just for the record, we discussed how Smudgeplot gives you an idea about pairing of your peaks. Would somebody tell me where the AABB smudge sits? What is pairing within GenomeScope? So what I would like you to object to is that A is in two copies and B is in two copies, which means that both of them are in this peak. And I was telling you they have lots of duplications, and I was pointing at this peak. So what's going on? Well, these are perfect duplications. Obviously, those are not picked up by Smudgeplots. But if you have perfect duplications, they definitely do also mutate. So there will be some bits within those duplications that actually did mutate it, which means that they do have one step difference between copies, which means that both those schemas would end up in this peak anyway. So this sort of gives you an idea about how much in this peak will actually be similar. It's not a precise measure, obviously, it's just some sort of idea, but it all makes sense. I think this is sort of the common theme of all the genome modeling. So your genomes do need to make sense. There's absolutely, you should not be waving hands on weird patterns. You should understand them. I'm not insinuating that you would do, just to be clear. Well, maybe I am. I don't mean to. So for case 17, you have this. Now I will increase k. Any guesses on what's going to happen? So do you think that the AB will increase or decrease? So do thumbs up if you think it will increase, and thumbs down if you think it will be decrease as a relative within relative intensity. If we increase k, decrease, increase, decrease. So it will increase. So 31 already we have that AB is 32%. If you go to 51, color scale doesn't matter. We now allow almost anything that is a valid name for a color scale. Will give you. It will you will see that the AB is now the prominence match. It gives you the right point. And the reason for this is the longer K you will choose, the more likely you hit the non-repetitive part of the duplication. So if you have smaller scale duplications, you will start kicking them out. While heterozygous sites, especially in a very homozygous genome, will have nothing around them. You can go far, 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 and you will be still fine. There will be still just one SNP difference. The story would be slightly different if you would have a very heterozygous genome, because if you once you start hitting the second SNP that is linked, then you will start having problems too. So if you would have extremely large 1N peak and a very small low N peak, you also want to keep your K down. Oh, keep your K down. Uh, okay. Do you feel like you have a bit of a grasp of how Smudgeplot can look like? How does it work? Okay, so I will just walk you through what is written in the tutorial. Then I expect you to launch Gitpod, run a bit of trial Saccharomyces cerevisiae data. It takes just higher tens of seconds and lower minutes. And then I have pre-computed for you 34 species from the Tree of Life of a beautiful display of ploidies. Then I already give you the well, I will explain. So I should have linearized my thoughts before I started talking. My apologies. So the one that is most stable version that is most used is double hang. It's by the way, the individual versions of the software are named by different types of windows. The original release was single hang, and now we're on Oriel. Who comes next? Who knows? I want to have a sliding window too. So this double hang is what is mostly documented, is what you will see in paper. Oriel is something that was released a month ago, but it was introduced in BG23 already, so it has some user base. And today we will be dealing with actually an unlabeled version that is the sploidy plot branch. This is a stable branch, so we are not tweaking it. We're not breaking the code. We're making sure that the code in this branch works. So you don't have to be worried that tomorrow you will not be able to do it again. But there might be a good reason sometimes to return to Oriel for some cases. So that's why it's not released as a new version. If it was just objectively superior in every single way, I would just replace it. But I will discuss a bit later about why we actually, what are the good reasons to switch and what are the good reasons to stay. And here I just described what is different. And when you will be running things, okay. I left here the downloading of the data. You don't have to do that. I actually pre-downloaded it for all of you. So if you launch your Git pods, there will be the data. Oh my gosh, I need to update this a bit. In the GitHub tutorial is definitely right. Wait, it's do I share the screen or do I share the?
You're sharing the screen at the minute, so you're all right.
Excellent. So if you go to the BGA Academy Smudgeplot, blah 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 blah, you can hit this button that will open you the Gitpod. You can see the slides that I'm presenting here. I will try to fix those small bits I pointed out. Right. And this is how we will be working with the yeast. So don't do what is in the talk, do what is in this tutorial, please. So it's just that because I downloaded the data for you inside of the directory, so you just need to know where they are. So the in this newer version, we fully switched to fastk, which is a KMA counter that is extremely fast, and it just it's about 6 times faster than double hang was. And so if you care about climate change and you don't want to burn CPU hours for no reason, just use fastk. It really makes a huge difference. With this, you just build the database. You can look at the manual to what exactly individual parameters are, but this is about the resource allocation. This is one of them is a threshold for KMA counting, and I'm actually never. And the other one is number of threads, and I never know which one is which because quite often you choose 1 or 4 for both of them. K is the KMA size verbose is to give you like a detailed output. This will generate your KMA database. Then you can use a different fastk tools to do different operations within database. I would recommend you to just look at it. Chin did a great job in documenting it. Hystacks is a toolkit that will allow you to take the database and just plot it's a histogram for genome scope. So you can just do this, and it will generate you a file that you can drag and drop to the web portal I was telling you about. This one. You will be able to see how the data looks like. Don't peek, you need to do it yourself. Then you will be finding all the KMA pairs. I think I actually think I have slides for the individual things. Okay. The workflow is that you will just fetch the code and the data, and you will construct the database. It's the fastk. Out of the KMA database, you will derive the KMA histogram that you need to visualize with a tool like GenomeScope. But honestly, if you like different tools of how to visualize KMA histograms, they're all fine. Then you need to select what you think is the error threshold, and then you will generate this file that will give you a list of frequencies of the KMA pairs, and then you will use that file to just generate Smudgeplot. This is just to give you a bit more idea about what the K actually does. More if you increase the K, more you increase I call it the complexity of the space, but that's not actually the right word. The technically right word is cardinality of space, which is sort of the number of elements that are in there. So on y-axis you have y-axis in log scale, and this is for increasing k of how many k must actually increase. It just blows out of proportion after 20, and basically more higher k you choose, higher fraction of your genome will be captured as unique sequences. But the downside of choosing very high K is that it will lower your coverage. Just simply out of the principle that if you have a read of 8 bases and you choose K2, you will generate 7 KMS. If you have the same read and you choose K7, you will have only 2. So you see that the KMO coverage of K equal to will be 2.5 or 3.5 times bigger than K equal to 7. Of course, that this is much less dramatic for long reads, but there is also some shenanigans with error rates and how they propagate to the KMR set, which we will not go into. But the general pattern would this suggest that so there in lower K you will choose, higher coverage you will have. So if you have a low coverage data set, you might want to go for things like 21 or 17. If you have a very high coverage data set, you can go much higher with your K and you'll be fine, and you will actually have much more robust inference because much greater proportion of your genome will be captured by these unique positions, right? So there is no objective measure of what K you should choose. You should look at your data and just show what is meaningful. But I would also say don't overthink it. If you start with 21 or 31, you will be probably fine. That's actually the range for what most of the genomes are done. Here at the Tree of Life, we use. Hey, I actually there came as in hundreds as well, and it works. If you have insane coverage, you can just blast it. It's a and it's quite fun too. But it's a the point is, you will not fundamentally have different answers. These tools are not meant to do the biology for you. They are sort of meant to give you some sort of sanity framework for which you can operate on your genomes. That you will not discover 3 years after publication that you have actually a polyplot genome, or that you actually have a failed sequencing run that has a very flat sequencing coverage without realizing it, and you just simply analyze the assembly. Like all those things have happened over the last decade a lot. So these tools are just meant to keep you sane, just for you to build the trust in your data. Okay, so from the database, the KEMA histogram is just the high stacks with capital G to give you the format that is favorable for genome scope. This part of the pipeline of getting the KEMA database, out of KEMA database, the KEMA pass, you will use already the Smudgeplot head mass, which with inside call this C code written by Gene. The L is the error threshold, so you'll be excluding everything that is below this number, and T is the number of threads. This is also the reason why I'm constantly messing it up, because I'm used to a different notion than Gene is. When you generated a KEMA pair file, it is actually fairly simple. It's again a histogram, but it's a histogram of pairs. So it is what it tells you that for coverage 10 and 10, there were 300 KEMA pairs. For coverage 10 and 11, there were 566 KEMA pairs, etc. Okay. And then we're trying to make it modular, but the modularity is all wrapped up in one command called all. Eventually, I would like even to move this bit into all, but that one is separate for now. And you basically give it the 2D histogram file and give it an output button, and it will just info you everything and generate you Smudgeplots. Okay? So I will finish with showing a few things that can go terribly wrong. If you have this kind of plot that is just brightest at the very bottom and looks like a tide wave, that just means that you had by far too many errors in your KEMA pair search, and basically you see absolutely nothing of your genome. This practically means that you have unusable data set with the L you choose. So the solutions can be that you will increase the L if it's meaningful, but it needs to be meaningful. This is the moment to look at the genome scope just to see whether there actually are any genomic peaks. If there are no genomic peaks, there is no way you can actually do any of the modeling. And I will tell you that it's even less likely that it will be successfully assembling the data set. So the best solution is just to get more coverage or cleaner data set. The don'ts here is just simply ask why your tool says it's a diploid. Well, it's very clearly a nonsensical data set. The tool will tell you what it sees. It sees nothing. Well, it's just, I guess, in these older versions of the software, we don't have implemented the like lack of signal model. It's hard to conceptualize. So basically, you as a user need to see that it doesn't make sense. What else can happen? Well, here I really got into strawberries. Strawberries were one of my favorite things. So when I first time really Smudgeplot, and then I tried to make as high coverage data as possible. So I started pulling libraries, and then it just didn't make sense. Look how weirdly misaligned those smudges are. You see that they just do not hold stoichiometry. What I did is I put two different species in one database. So these misaligned smudges that are not even in coverage ratios, so which means that some labels fit, some don't, is indication that you probably pulled together things that were not supposed to be together. And so solution there is just, again, look at genome scores, that it has same number of evenly spaced peaks, and separate your libraries. The don't is exactly the same as last time. Just don't read this label and say, oh, he's deployed. The other issue can be just simply on the side of Smudgeplot, that if it will just infer you wrong coverage, like here, it will just give you this messy annotation. So it just underestimated the coverage a tiny bit, and this smudge that is all definitely AABB is just half annotated as AABB and AAAB. So this is just wrong. The newer versions of Smudgeplot are much more robust against that. So solution here is just use newer version. But you can also tweak the expected coverages. And again, you need to make it consistent with genome scope. So don't just read diploids without critically looking at the data. That's actually like number one issue people are having with Smudgeplot, is that they overly focus on this part of the plot and not enough on this part of the plot. This is a different case of the same mislabeling issue. The newer back then we didn't have a correction for the relative position, the x-axis. So sometimes you had a triplet smudge in a diploid position, and so this is impossible now. So here I would like use the newer version, and this is actually if you do very fine tuning of that very same data set, this is how it actually should have been done. And you see that it actually is a tetraploid, that there was something hidden over here, that it was just by a choice of parameters been hidden. So that's actually where I would like to leave you for now. I don't know where it disappears. Oh, here it is. Okay, I'll copy paste it again by the very end. So do you all see the presentation? That's good. So I would like you to find this Google Doc, open it, because you will have there the list of all the genomes I've fetched for you. One of them is the octoploid strawberry. So I guess
Could you maybe paste that into the chat, the link?
Oh, I can do that. And all those data sets have corresponding directories in Gitpod. So if we go to Gitpod, ooh, that's not Gitpod. Okay, oh, it was start a new one, right? I don't want a new one. I already started one. By the way, the setting up, I don't know if you launched the Gitpod already, but it will take a few minutes to set everything up. The Gitpod is actually doing everything de novo. It's a vanilla Linux environment. It just reinstalls everything. And by the way, if you're wanting to deploy these tools in your local environment, I would heavily recommend just look at how the Gitpod was constructed, which is in the small YAML file in the repository, and it just gives you very precise instructions of how to actually install it without human interference in a vanilla environment. So it cannot get more, how to say, the deployability cannot be much greater than that. So I see that I run the Smudgeplot on everything here, but you in your versions you will see that each directory that will be indexed will give you one game pair file and one histogram file. So basically, all I did for you was to run the fast kmart for you, just because it's very repetitive. There's not all that much to learn on that bit. It's much more interesting to just do the Smudgeplots, look at them, and make interpretation. So that's why I wanted to split it up. But the tutorial has the Saccharomyces data. So if you feel like you would like to try it, it's just do it. It will take a few minutes. So now I will give you about half an hour in which I will still stay here and will be answering your potential questions if you get stuck. I hope that within this half an hour you will do a few trials, you will do a bunch of fails, you will read the error messages, you will think for 15 seconds, try to fix it, and then ask a question. If not, and then we can together look at what you have found. So please do write your name into the genome you work on, so you don't work on the same genome as any of your colleagues. And you can take as many genomes as you want as you go through them. And then here we have this big table where you can just be pasting the pictures of genome scopes and Smudgeplots. You can play with different case if you feel like, with different L thresholds, try to document it. And your assessment of what you think is diploidy and what's going on with the genome, you can just write here. Okay, and then in this half an hour, we will together go through some details on how what's happening with Smashplot and what's up with all those bloody versions and why am I talking about them. And we'll be talking about all these. Oh, analyzing the potato. And then we will going through these plots to sort of get a hang of what we have actually done. Okay. Damon,
Hello.
I just noticed that the BGA webpage is has the outdated it's a BGA23 tutorial. And is it automatically fetched from the README file?
Yeah, no, it's not automatic with this one.
Ah, I see.
I I need to update it now anyway because it's
Oh, oh,
on the
oh,
YouTube stream asking for the Discord link, and you can't put the Discord link in the YouTube chat box without it getting censored. Um, so I need to update the website now anyway. So I can,
yeah, or you can just put in the tutorial link to the GitHub page so people read the README file there. So it's on a single spot
yeah,
for now. We can paste it back afterwards. But I think right now it's a safer way because if we will have to make more edits, at least there will be only one spot where we have to do it.
yeah, okay. So you want the README shared?
Yeah. That's the. Uh, I don't know. I just send you the link. Yeah, you see. Does everybody see the tutorial that is here on the GitHub README page?
You should be able to open it inside the Git pod as well.
Yeah, that's also true. That's also true. But we should develop a better system of how to distinguish between versions. I feel like it's getting slowly quite messy with the BGA 23 and 24 if they share the sessions.
Yeah, the idea was to have branches per year, but obviously because we had a different GitHub organization entirely last year,
Mhm.
it kind of got messed up a bit. From now on, it should be there's a BGA 24 year branch, 25 branch, and whatnot. So hopefully that should help. I mean, actually, next year, hopefully we should move to an entirely new website that will be a lot fancier and we'll be able to distinguish much more easily.
Yeah, but funny enough, the yeast data specifically, I use almost everywhere. Like there's almost no Kima tutorial where I wouldn't use this specific yeast data set. It has the right amount of messiness, fun deployed. It's a good data, and it's quite small. Good data to work with. I also corrected the slides, I think, mostly. Yeah, I think all the paths are there. The download links are commented out and replaced by where they are located within the Git pod. I'm unmuted the whole time long. Well, never mind. Good that I wasn't saying anything. Do people feel like they got somewhere? Would you like more time then? Okay. But would you like to also share your problems? You should not get stuck on silly things. Do the interesting bits. It's enough work to get stuck on the interesting bits. By the way, the easiest will be if you will paste there the whole image. Just that simple is just screenshot it and just paste it, or just if you just right click and do copy image, you can just paste it and just make it smaller so it's the same. Thank you, Kiwi. Alina. Would people like me to do one of them in front of everyone?
Yes,
Okay.
please.
Okay. Uh, I'm showing you the whole desktop. I hope I will not hit anything strange. But the reason I'm doing this is because I would like to go by the tutorial just like you. Okay, I don't care any of that. So, inferring coverage and plotting Smudgeplot. Okay. Uh-huh, uh-huh. Uh, okay. So, git plot. Yep, I will make it bigger, so not that big at that. Hey, look at that. So, it just needs in file, and then it should work. So, where were the files again? Nope, nope, nope. Okay, let's just close all those tabs we don't need, huh? Oh, here is the data. So, okay, everybody sees this data. It's it's just simply the Git port just saves the whole repository as it is in the name of the repository. And within the subdirectory data, just put all the individual directories. If I will look at all of them will have inside a hist file and this SMU file. Oh, hey, this one is missing the hist file. Well, I guess Strawberry is below genome scope. Hey, this one is also missing the hist file. I'm sorry about that. Is there anybody who's actually doing Nettle? By the way, did you know that this one is a Nettle with Picadieke? Um, if you well, okay, I will get back to that in a second. Hey, even Potentilla Anserina. That's also a very nice plant, by the way. Okay, so I will pick one. Which one do I pick? I will go. Hey, this one I really like actually. I don't even know what it is. What does it look like? Okay, so it's a carrot, I think. Oh no, it's just oh, never mind. I cannot tell plans. Exposing myself in public. What was I thinking? Okay, so that's which one was the number again? Gosh, 13. So because I'm lazy, I will just find it within the data panel on the left. There's 13. So I will download the histogram because I want to see the. Mhm. This looks good. So let's go to Genome Scope webpage. That's not Genome Scope webpage. It's Genome Scope webpage. And drag and drop the histogram. Go. Submit. I'm glad that it was acceptable for you. I run the default because actually ultimately what I truly want to do is to see the histogram. There, you, you can think about it more later once you actually know something about the genome. The first and last thing, like the most essential bit is just to actually see it. So one major peak, lots of smaller peaks. The coverage is about 22x. Okay, that's all I wanted to hear. All with me? So let's run Smudgeplot. So what we will need is this. So there was Smudgeplot with BY. The subcommand was all. The positional argument was the text file. And let's not be messy and leave it in the same directory. This is just an output pattern. Oh, wait, this everybody sees that. What happened? What happened? What happened? Oh, file not found. What do you mean file not found? Is it because
I think the first letter of the file, you've got LA.
that will be it? Good. Panic in village. Okay. So what's happening? It gives me lots of logging. That's good. I like logging. Oh yeah. It might relate to the fact that I wrote in the logging. Oh, it gives me what version is running, which is some sort of development version. The task zone, loading data, all good. It gives you some numbers about what is masked as an error. It's about 5% of the data. Why is it 5%? It is. It's inferring the one and coverage about 21x. Are we happy about that? Is it consistent with genome scope? Is it clear consistent with genome scope? Good. It gives you sizes of the individual smudges. It's also good. Plotting, that looks like it plotted well. So let's take a look. So we didn't talk about the centralities, but there is a measure. Wait, showing nothing. Is it broken? Oh no, it's not broken. Okay, good. This is a metric that is actually optimizing. It's giving you an idea about what coverage it fitted. So these are the coverages that were tested, and this is how good the fit was, and this is where it converged. This is the reason why it's actually not released yet, because this metric is not satisfying enough for me. It doesn't converge always right, and that bothers the heck out of me. And this is the research that is ongoing. But it works quite well enough for majority of cases. So it's not like I should not share it at all. It's just that I would like it to become bulletproof. Okay, what people think? Can I have some people communicating now? Uh,
Yeah, that was great. How do we download to how do we view it ourselves?
wha- what do you mean how you view it? Like
I can't see it in view the output. There's no PDF here to do a screenshot.
well, you should see it in the panel on the left. Like you see in the panel on the left, you have all the files. So if you run the command, you should be able to see the PDF file. Just click on it, and it will show up like this.
No, it's all just blank.
It's just
Must be me, my setup. Sorry.
okay. I will take a look.
I'm sure. I'm sure it's other people.
Does anybody else have the same problem of seeing it blank? So you see this your Smudgeplots. So I guess PDFs are hard to, not too hard, but where is the file? Damn it, screenshots. There it is. 13. There you go. That's what I hope people would do. Fill me this with Smudgeplots. And now looking at this, I feel like that's definitely not a diploid. That could be probably a tetraploid because this is like where it sort of starts trailing off. So there are no clear smudges above tetra, but there are just by far too much structures up here to just think it's a diploid. It's not as easy to say that I guess it could be the tetraploid or hexaploid. These would be two models I would consider in this case. So what I would do is just now go back to genome scope, find that file again, go size 6. That's not the camera reuse, that's 31. Good, give it a right name. We know that one of the coverages is 21, so it just has easier time converging. You don't have to give it the prior, it will find something anyway. This time it will be fine, but it's nice to have the algorithm if you can. Man, that actually doesn't look so bad. So now we're talking, right? Assuming hexaploidy and inferring the coverage 20.7x, we can tell how big the genome is. We can tell the genome is 1.3 gig, and this is per haplotype, which means that the total genome size would be 6 times the number. And now you know that if you start assembling it, what to expect. If you will assemble 1.3 gigs, you expect that you assemble the haploid representation of that hexaploid genome, if it's a hexaploid genome. What you also expect is that if you map back reads, you will see the allele ratios up to 1/6. And this is pretty neat. This is the sanity I'm talking about. It all needs to make sense together. It won't ever. These numbers need to be close to each other. Like it won't be ever super precise. If you will assemble 1.25 instead of 1.3, well, I guess that's understandable. Of course, the genome size estimate is an estimate after all. But it looks okay. And you can also go back and do the same with tetraploid. And by the way, the genome scope runs only up to hexaploid. So if you're trying to fit an octoploid or a pentaploid, sorry, decaploid, I would recommend to just half and deploy it and then just multiply the numbers. Because if you fit a tetraploid model to an octoploid genome, you will get twice as big genome. Oh, sorry, twice. Yeah, twice as big. Wait, which way around? I will not be telling you now because I will get it always wrong. Look up the equation, it's very simple. It's just that I remember it's factor of 2, never in which direction. Um, there was a chat thingy I didn't see. Oh yeah, but this is the tetraploid. Hey, that also doesn't look like it. But again, hey, look at this. It gives you two very distinct predictions on the haploid genome size. I'm pretty sure that if you will actually assemble it, you will know immediately which one it is. But assembly itself won't tell you. The genome scope itself won't tell you. Smudgeplot itself is just giving you some idea that it will be something higher because whatever it is degenerated. Of where was it? Oh yeah, here. Um, when you're doing these plots, if you're interested in seeing those all the weaker signals as well, it's easier to look at log scale. If you want to see the real core power, then you can just look at the linear scale. So uh, this potato looks very different. That doesn't mean that you actually managed.
Yes, thank you.
Good. I was about to ditch people and come to you for a second. What did? Well, never mind. So I would propose that you will low key fill the rest of the table while uh, some of them look good, huh? That just for the record, they're not the most representative genomes out there. What I did is of the two, wait, no, actually, it's a lot more than 2,000. About I have like 3,500 genome sequence with PacBio, and of those, I picked all those that had predicted ploidy between 3 and 10. And I excluded lots of things that I thought that are boring, and I just like kept like a good representation of the hydroploids. And I picked a few mosses and wasps that are monoploid as well, so just it mix in both directions. But like all I'm saying is that all you can will be seeing here is funky. So oh yeah, what I wanted to say is oh yeah, I see. The Gitbot is not always loading them in time. Oh yeah, I see. I think Katya has the same problem. It's a. I guess you just need to be.
Can also just download the plots.
Oh, you can download the plots.
Yeah.
That's a great suggestion. All right. Oh, hey, that looks good. That looks good. Try to spell out on the right. What do you think about the genome? It will be helpful for you to hear my feedback. I think. I hope. Maybe. Did you hear that? Okay, I think I will let you work, but I will continue on talking and uh, and then we can in the end spend some minutes on the outputs. So mine seemed to be okay before, but now I get this error, command not found. Oh, so that's something wrong with the environment. That the Smudgeplot PY should be installed there. That would be very hard for me to debug without actually seeing the environment. If you, like the worst comes to worst, you can just trash everything and just launch new Git pod, and it should be okay again. Okay. Are you ready for this? I, this is not a very well practiced part of the talk because I'm now just doing a live dissection of how Smudgeplot is developed in front of you and sort of trying to walk you through what are the challenges and how they are solved right now and how where we're going with this and why we don't have the satisfying live release. It just seems that I'm the only one who cares about it, but it really broke me inside not being able to do that. I'm over dramatic. Never mind. So already a few weeks back, I had this update for Smudgeplot. So now Smudgeplot look like this. Using exactly same data, using Oreo, you get Smudgeplot like this. Is there anybody who likes the left one better? I hope not. It's messy. It's messy, and it took me a while to figure out what is actually going on. But so what? Um, so oh no, why do I do that? Yeah. So I will walk you through all the changes. So the double hang is the one that is in all the publications. And the switch to Oriole is mostly switch of the internal engine for switching gamer pairs. To most of the users, there will not be a very significant visual difference to what they will actually see in the plot. But the massive difference in it now it scales to any genome size, but really any. You could do it on Holly or Mistletoe, and it will still work. It's linear. Um, and it's fully parallelized. You can run it in cluster. They will not preoccupy your resources for all too long. It's a really good algorithm. But what it means is that we unfortunately had to completely marry to FastK. I guess I liked philosophically to be open to any gamer counter that is out there and just simply operate on any gamer dump, which is not the case anymore. So the user base of Smashbots is now expected to switch to FastK, which I think is what Jin is very satisfied about. But I would really encourage you to do so. It's so much better, and that's it. So Oriole is basically double hang inference engine built on Gene's way how to infer gamer pairs, and that's the one that was actually presented in BG23. The new implementation is cache coherent. It's 6 times faster, fully parallelized. And the small change that actually makes a weirdly big impact is that we used to report every single coverage. So it would just give you 6,500 lines with 2626. And then it would give you 13,000 lines with 2627. So it would just simply, you would have to calculate yourself the histogram. So this file would have 300 megs instead of 300K. So it's that was like a silly change, but now I think it's like a lot more readable. But then we started plotting, and we just found out that the spectrum is still there. I guess it would not disappear, right? And And after a very long time of thinking, looking at it, I just figured out where it came from. It's just that while the x-axis is a ratio, so it appears as a continuous variable. It's actually a fake continuous. So in this plot, the L, the error threshold was 4, which means that the lowest two k-mers that will be in there will be 4, 4. And those will be the only possible pair for coverage sum 8. Everybody with me? For the coverage sum 9, there is also only one option, 5 and 4. For coverage sum 10, there will be 5, 5, and 6, 4. But if you will then now think about it, this will give you just only one ratio for this coverage, one ratio for that coverage, and two ratios for that coverage 10. And the two ratios will be 0.5 and what it is, 4 over, it's 0.4. So it's semi-discrete. Like this cannot be anything between 0 and 5 or 0.5. It will be always at what the fraction possibly can be, right? And lower coverage you have, more semi-discrete it becomes. If you have very, very high coverages, it will actually become more or less continuous. But at the very low end of what is meaningful Smudgeplot, it just becomes this very, very speckly, just because you have a very different number of points that fall within each of those squares. So and this is a visual representation of that. So on the left panel, you see how it would look if we plot every single data point. On the y-axis, and on the right panel, you see how it looks if you just cut the data in squares and aggregate them. The idea was, it all started by me using some high level packages in R that was just like the heat maps and things like that. And this is what they do under the hood. So it somehow never occurred to me that I should bypass all that and just make the plotting on the raw data and just plot every single bloody square. And that is the solution. The solution is not to bin. The solution is do not transform your data if you don't have to. The left and right panel are the same data set. So if you get rid of this stupid sampling bias, it just becomes beautifully smooth and continuous. It's so much more readable. It has a lot more other challenges. So for instance, the algorithm for searching for local peaks was based on the neighborhoods of the 9 squares around each of the squares. So we're sort of just saying, hey, is it local maximum? And this becomes here more difficult because what is a local maximum? They're not squared. Each of the lines will have the cuts on a different places. So basically, it's the same plot as this points, but instead of just plotting as spots, because it's very hard to see on a wide background, you just expand them as bars, and so it fills the space. But it's the same principle. So, and also higher you go, the smaller squares you will have, but they at least will have fair density. Each of the pixels will represent exactly one Kano pair. So yeah, it looks good. It got rid of the speckliness, and from the sort of strangely messy smudge plots, we get this, very elegant and readable, sleek smudge plots. I turned off the histograms because I just couldn't be bothered with it, and I just found out that actually nobody complains about it. If you would feel like you really, I think we will eventually return it because I think it's part of the visual identity of Smudgeplot. It just looks pretty, but I honestly don't think it's actually really useful. Do tell me if you think otherwise. So what did we come up with instead of the algorithm that we have in the old Smudgeplot how to infer coverage was a local aggregation that is based on Manhattan distance because all these k-mer pairs can have a certain distance from each other, right? And because this is such a easy discrete space, I thought that Manhattan distance would be actually fairly appropriate. So I just say that I will be searching for all the local maxima within certain sizes of neighborhoods. So I said, I think I ended up saying 3. So if 2 points are within the range of 3 or distance 3, I would just say aggregate them together if one of them is bigger. If they're more than 3 and they're all local maxima within their neighborhoods, you will initiate 2 different peaks. And if you do that, and you then color this smudge plot by where you annotated a peak, you see that it actually very nicely cuts the space in what you would actually thought are meaningful smudges. But if you will start doing it a lot, you will find out that it has always more or less the same shape. So what we started doing is that we take all these bottom smudges, because that's always error and something, and we just use this as a filter. So we locally aggregate just to filter out errors. And for the rest of it, what we will do is we will just project this grid on the data like that. And the beauty of that is that you can actually project that grid with any expected coverage, because every expected coverage gives you an exact position of the whole grid. And if you do that, what you can do is to calculate that centrality, which was the centrality point you have seen seconds ago. So that just means that you will just calculate over how central is that smudge sitting within the fishnet. So I stupidly never got around to make the fishnet with obviously wrong coverages, but you can imagine that if you stretch the fishnet with half bigger coverage, and they will be cutting through the middles of the smudges, the centrality metric would be very poor. The bulk of the data within each of the cutouts will be on the edges, will not be within the center, right? So the centrality measure can be used to just detect the reasonable coverage, and this is how it looks. I just wrote an algorithm for mostly tree of life data that always target the the 20 to 40x coverage. So by default, we're exploring this 10x to 60x, and it's just sampling more denser where it looks good. If you have data sets that look different, you just need to adjust the ranges, which is parameterized. So actually, I wanted to show you one more thing. I don't have the one more thing. So I wanted to tell you where is the actual problem with this. And I think I will show it on the strawberry. Strawberry, go back strawberry. If people get dizzy from, that is the strawberry. So I'm not sure if it's intuitive for you, but higher coverage you have, more variation you will see. So the same amount of data will be spread over the wider peak. Which means that while at the bottom part of the fishnet, the cutouts will be actually super nice, and it will be very well separating the smudges. And the top part of the plot, it will be less so. And why is that? Well, because the cutout is based on the sort of most likely assignment given coverage, given all the peaks would be have the same height. But that's obviously not the case. If you have two peaks, one is tiny and the other one is big, the big one will have bigger variance and will be basically overflowing over that other peak. And if you do fair cut assuming the same, you will cut midpoint, right? But all those things that overflow will be in the wrong bucket. So in this case, in this strawberry, you have this very big 6A2B smudge, which is, and the whole thing, I guarantee you, it's all from the same ploidy. All the variation comes just from the sequencing coverage variation. And if you do this trick fishnet cutout, you will cut a piece of that smudge into one higher ploidy, and cut of that smudge in the lower ploidy, just simply because if all the smudges were present and all had the same height, that would be the most likely assignment. And that's unfortunate property. That's the one that irks me. That's the one what stopped this release to happen. So what we're trying to find out is how we can define a model that will actually be able to capture this property of the data of increased variance over the high coverage. So we are just trying to find an explicit polyploid model that will allow to just be more explicit with everything. So I don't know. It's how understandable this bit was, but it's I hope that you at least get a gist of where we are at, and we're actually very far. We learned so much over the last few weeks, and also what kind of Smudgeplot, they look amazing. Um, one note is that I stopped reporting ploidy for now, because I think it's actually somewhat very misleading. What you should think about are the intensities of the individual smudges. That's basically, we don't have an explicit model for the ploidy. We don't actually really know if it's a hexaploid that has a certain level of degeneration. What is actually the explicit, like what is the expectation? Do we really expect the hexaploid smudges to be brightest? I don't know. Like I think it's very non-trivial, and people want like simple answers. But this is genomics, and how many genomes we actually seen of the diversity of life. I think it's unreasonable to expect a simple answer without understanding the data. So that's why I, at least for now, before we will have a good model for the diploidy, I would vote for not reporting it and just let users to wrap their intuition around what they're looking at. So this doesn't look like a diploid at all, right? But at the same time, the diploid smudge is still the brightest. So if we would just have an algorithm that says the most common smudge will be the one that determines ploidy, we would say it's diploid. But that's, come on, obviously wrong. So that's why I'm hesitant of writing some simple rule that will just make a label, because people then focus so much on the label, not on the data. And it's not easy, I know, boo-hoo. These are genomes, that's why it's exciting, no? Okay. So I will just finish with a bit of pop art. I love making Smudgeplot in different color schemes. Do you think it will sell for some money? I think it should. And I would like to give some acknowledgements before we go through this end of the talk. I will look at the data. But I would like to thank a lot the whole Smudgeplot community, because we have lots of very active users that are helping. Like they really immensely affected the way Smudgeplot was developed and where it is today. So I think it's really important to acknowledge the role of community. Be good citizens, submit issues. It's really appreciated, and especially when people are polite. If when you don't approach developers as somebody who's supposed to give you a service, it's so much nicer to deal with it. Big shout out to Gene for writing that Came Passage algorithm that was really game changing. This is what motivated all the newer developments too. Sam helped a lot over the last few weeks with tidying up the code and just flipping everything to Python. So right now, the Python interface is still calling R inside, but when we get to the sliding version, it will be all fully Pythonic. And that's all Sam's doing. And the inference is not easy. I was gradually getting more and more people involved with different ideas, and none of them was perfect enough. So now we have a long list of people that helped with inference. But specifically, I would like to give a shout to Tiani, who actually really his stubbornness and arguments made the inference work. Like the one that we see is the one that we together came up with. Uh, if you're into sequencing technologies, you know that PacBio does lots of homopolymer errors. If you do homopolymer compression, that was the idea that the signal should clear up. But one thing that will happen is definitely that the coverage will increase, because efficiently what a homopolymer compression does is that it will actually increase the K, because if you compress it, it will be just with the same K value a longer stretch of sequence. And the second bit is it does not really clarify the signal. So I don't think the homopolymer compression is a thing for you. I don't know. Oh, that was a supplementary slide. I don't know. Sorry, when I've seen it, I could not share it, but no, that's it. That's it. Let's now take a look at the genomes. Did you have good times? So, my very, very favorite part of being at the Tree of Life is that I feel like I'm in the candy store every day. That we have this Slack channel that is just popping all the new sequencing data that looks like that goes through the sequencer, and we have all this automated QC which runs genome scopes and Smudgepods and everything. So you can immediately every single bloody fungus you see is like, Jesus, what is this? Those pigs are weird. So it's good, and I'm very happy that I was able to show you some of the weird ones. Oh boy. Oh wow. What? That's not a strawberry. What is this? Oh no, that's the Tree Murray. What is that? LA is
Monocot.
it's a monogon. Who would the author be like to ever elaborate? So
Sorry, I did that one, but I think I pasted it in the wrong one. Let me just quickly see what I did the data on. Sorry about that.
okay, if it's associated with the wrong ID, that's actually okay. As long as these two are matching. Are they matching? They look like
I did it on 4, not on. Yeah, I did it on 4, but I typed in 5. I see there. Sorry.
No, it is in 4.
But the top table I said 5. So there's where the confusion comes in.
Oh, I see. Oh, that's fine.
Sorry.
So, what is the one in coverage by genome scope?
The one in coverage by genome scope was the 71. So it's basically double.
And Smudgeplot?
36.
So are they consistent?
No, but that was for the genome scope was set to 2n, and with that is half of that. So that's why I thought maybe this suggests more of a tetraploid, not a diploid. And then with that
Good
being half,
thinking, but it doesn't work that
sense.
way. That doesn't work that way. So it works that way with genome size. It doesn't work like that with the one in coverage.
Oh,
So
okay.
It would if the real heterozygous peak was here. Do you think it's there?
No, it doesn't look like that.
I don't believe it's there either. So if there was a bit of peak over here, we would actually see a gentle smudge over here as well. And we don't. So what I think is, regardless of what's deployed, one in peak will be one in the coverage will be 171x. So if we would, so if basically this is not all that wrong, except that we need to relabel the smudges. So this one will be AB. This one will be 2AB, 1B. This one will be 2A, 2B. Everybody with me?
Okay.
If you will be halvening the coverage, you will be dividing all the labels by 2.
Okay. Makes sense.
So even without, we could rerun the Smudgeplot so it has the correct labels, but we could actually look at it already. So it seems that actually might be tetraploid because there are tons of KMs that are there in 2A, 2B. But again, this is one of those annoying edge cases where you have a lot of higher level coverage, higher level, higher ploidy KM pairs. But the strongest one is the one that is diploid, the AB. So ABB is actually the AB, right? So what would maybe make sense is just to increase K, just to see whether the relative intensities of them would change. But of course, you cannot do that because I already give you the SMU file, so you would have to rerun the database and with the right K. But anyway, this looks good. Actually, I have a sheet with answers. So the number 4 is predicted tetraploid. Oh, that's wrong. That would be. Wait, no. Which was the number 4, not 24? Oh, it's predicted octoploid. No, I don't think that's octoploid. I think that's tetraploid. I think that's tetraploid, and I think that's allotetraploid because the strongest signal comes from 2 and 2 haplotypes. Okay? If it's an autotetraploid, you expect that the variation will be always carried by rare variants. So B, where the B will be in different cases in different haplotypes, is the expected structure, or like as a predominant structure. So I would just say this is probably autotetraploid. Oh boy, so you see that this is actually not an optimal sequencing run. Why? because the error peak is blending with the genomic peak. It's not tragic, it's probably assemblable, but it's not what we would love. The Smudgeplot looks actually quite diploidy. Juniper. Is it Juniper? 6.
No, that was 7.
7. Wait. Oh yeah, 7. That's also meant to be octoploid with 18x coverage. Yeah, see, I don't think this is octoploid. So this was predicted octoploid, and I would actually say this is probably diploid. Prediction versus observations do differ quite often. You would give both information. Oh, you like the information? Okay, I will return them back, the histograms. So then bear with me, it might take a moment. Or if you feel like you are comfortable enough with Python and you can just implement them yourself, So this one is meant to be tetraploid, but I think it's probably diploid. There's absolutely no signal of polyploidy. Sometimes what can happen is if you have very old or degenerated tetraploids or polyploids, is that you actually, on a camera level, it can be easily diploid. But this is still informative information for you. When you're assembling and it's on camera level diploid, you will be definitely separating the haplotypes everywhere, absolutely everywhere. So if you don't see tetraploid smudge, you will be practically dealing with diploid. Even although if you will then just take the genome and self-align it, you might be able to find the corresponding homologs. So basically, Smudgeplot is for kind of like a recent camera base. So this is the tetraploid hexaploid. We discussed that one. I'm not clicking on links. You should have pasted image. What happened here? Why is it so dark? Any guesses?
Is that the base one, not a log?
So that one is not a log. And one more, the error threshold was chosen 4, which is pretty damn stupid given the data. But somebody just run the analysis with the same bottom thresholds for all of the data. So basically, you see that this big chunk of red stuff got into there, and the sequencing errors just happens to be similar to sequencing errors. So you just have tons of those schema pairs that actually are unique. So basically, just because you will have these probably 600,000 error schema pairs, it just normalizes by this one value at 4,4, and it just renders the rest of the plot black just because it's linear. If you look at the log, the log plot, I like to look at the log plot because then the fact that you don't have to be so cautious with the errors. If you want to have the linear plot, which is legit, then I would recommend just being more cautious about cutting out the errors. And yeah, okay, I don't. If people need to run, they can run. I can otherwise scroll through the rest of the Smudge plots. I don't know how people feel. Thank you, Damon.
Cool. Thank you. See you all later. I've got to go and run the next session. So yeah, see you all later.
Yeah. This one is to me like a beautiful textbook example of a tetraploid. Yeah, absolutely. You see that although the most frequent smudge is again AAB, so it's probably a bit of the generated tetraploid. It's just there's no universe where a triploid could have had a tetraploid smudge. That's what I'm saying. That without actually thinking through of how the ploidy, heterozygosity, and duplication levels in the genome cross interact and write an explicit model for that, you won't be able to just have like this like easy label. The easy labels would come only if we would have a meaningful model. And we're working on it, but we're not there yet. Actually, I can show you how far we are. It's on the whiteboard behind me, by the way. That's a different story. Potential Alcerina, that's predicted tetraploid. But again, that to me, that looks diploidy. That would quite easily be diploid. If it's a tetraploid, then degenerated. Again, from Cable perspective, I think that's actually diploid.
it is actually there are two different chromosome morphs. So they're tetraploids and diploids, so they were obviously sequencing a diploid. So
we
I
actually
looked
don't
it up.
have.
Yeah.
Oh, that's pretty cool. So the thing is, at the Tree of Life, we don't have a luxury of doing tons of preliminary analysis on the samples we're sequencing. So we find a potentilla, we throw it in a sequencer, and we see what comes out. We don't really make sure it's a diploid. But I'm maybe with potentilla specifically we did because it's such a common plant, but in general we don't. It definitely when we're collecting biodiversity samples, it's biodiversity samples. But see, it's pretty cool. We had a prediction of tetraploidy and data. We'll look at the data and what do we see is a diploid. Cool, no problem at all. Dravern. That's a dicot of some sort. Everything that starts with D is a dicot. So a planty boy. Huh. That's funny, huh? Is it? Draba Werner. Well, okay. It's a cabbage. Never mind. Coverage in Smudgeplot was consistent with genome scope, and genome scope for N looks better than. Yeah, see, it's a genomes are annoying that they evolve. I think again, this is not a recent tetraploid, but this easily could be tetraploid. It has it. These are the annoying in between case. I actually think we will more and more we will be looking at genomes. We will see those in between cases where there are signatures of polyploidy, but it's not that simple. And actually, this species, I don't know if what is confusing to me here is what's the proportion of cables there in one end peak? That's sort of outrageously high, right? Is this really that heterozygous? Is it possible? I would actually say that it's more likely that the one end peak is really misplaced, that it will be actually fairly homozygous. So if this would be actually probably completely homozygous, then we might have just taken, unfortunately, one that was sort of a submated or something that there is absolutely no signal to pick up. And then this would be tetraploid smudge, and this would be hexaploid smudge, and this would be octoploid smudge. But my personal guess in that case it would be that it's a diploid. Yeah, I don't know. And somebody cut out the legend. So the legend is actually quite useful for knowing how many of those cables are actually in there. That is a bit that I actually still didn't manage to fully integrate, but what I would like to do is to start comparing the absolute values of the cable pairs versus the relative sizes of the peaks. This is something this is where I'm going with that idea of making a more explicit model, because I imagine that if there is no heterozygosity, the overall signal will be much, much weaker. See, so these are very low numbers. That's overall a very weak signal. So I would actually believe that these are the same as the haploids or the homozygous diploid, because I have hard times believing that this is one NP. All with me? Okay, again, here we're claiming that the giant peak is the one and peak. Three to be. I actually think that one might be yeah, I don't think so. Is there a universe where this could be a tetraploid? So imagine again a scenario of something plant. Okay, so there is very little heterozygosity to normalize by. Even these numbers are not super high. To me, it looks like a genome with quite a bit of duplications, like a classical diploid genome with very homozygous plant genome with lots of duplications. You see that like all these methods are based on some sort of assumptions about the genome structure. If you like plants are specifically nasty for not behaving well in their heterozygosity. They have both extremes of very, very high when if you run into hybrid and very low if you're running in a selfing plant. So you would have a lot more educated guesses if you would actually know more about the plants.
Actually, I think, Camille, here it's the same again. It's a plant that can have 3 different levels of ploidy, and they obviously looked for one with the lowest ploidy level for sequencing. So it should be a diploid, actually.
Yeah.
But yeah.
So we actually mark. So if we knew the ploidy, we would mark it in the system. It was not marked in the system. So I actually think that this was just a lucky coincidence again. Okay, who did this one? This is a very unhelpful plot, isn't it? I actually think this one. Trifolium dubium might be the same. It gets very planty, huh? I will just cruise through this one. There's not much to discuss. So, bombus. So now we're in an insect world. So this is a male of haplodiploid species. So again, if you would look at the log plot, you would see the smudges that are actually in there. If you would see the scale, you would see that those numbers are not insanely big because they're just, again, showing the paralogs within the genome. You also see those like blank spots within the smudge plots just because there are no chemopairs of that coverage combination. And, it's still pretty fun to look at it because it just gives you a detailed structure of what genome, the relative copy numbers of things that are similar within the genome look like, but it's not predicting euploidy. And the same here, this is also a haploid species. 41. Yeah, see, so here it actually underestimates. Wait. That's about 80. I think this one is wrong. This one in coverage should have been 80, approximately 81. And this would be one AB match because this is a haploid genome. If it was homozygous diploid, then it would be correct. I think this is also an insect. This is a wasp. This is a wasp male. Oh, wait. Is it a wasp male? I actually. So wait. Maybe now I will also show you the last thing. There's this magical webpage called StoreQC that contains all the QC plots of all the tree of life genomes, which is bang. It's so many genomes. And all sorts of funny biodiverse data. Oh wow, pentaploid. We will go back to that one. Wasp. So that was the wasp number 1. That is a male. Okay. Problem solved. If it was a female, then we would change the interpretation. Again, know your data. The biology is important. Not by Rose. Where's the Rose?
Number 16.
16. Oh my goodness. So I wanted to say, so this Rose is predicted hexaploid. But no, that is very clearly pentaploid. This is one of the cases where it's very, very crispy. That's how we like our smudge plots. Good. Any questions, comments, anything I can help with before we close the session? 11 minutes over time. It's not that bad.
If I see an error in the genome reports from Tree of Life project because the Smudgeplot was misinterpreted.
It's, yeah,
Is there anything I should do, or is that going through your lab and you will just say, no, it's not an octaploid, it's just a diploid with wrongly annotated peaks or something?
so where do you see the error? In TalkQC or in a genome?
I think it's in TalkQC here.
So TalkQC is fine because all those are automated plots. So
Yeah.
it goes without saying that you need to take it with a grain of salt.
Okay.
I promised Shane that I will give him a full list of what I actually think about these specific genomes because I did pick up a good set of freak show and I'm actually very pleased that they approach me quite often with the funky ploids just to give my gamer views. So I think some of those will get updated in there. The rose is cool, isn't it? Have you ever seen a pentaploid?
Well, I've worked with it actually, or worked with data from it.
From this specific pentaploid?
From this, well, from the whole genus. So
yeah.
What is it called? The subsection.
Yeah.
Belongs to, and this is all pentaploids or hexaploids. Hexaploids are usually hybrids between different pentaploids. So yeah.
How does that work?
Completely crazy system. Yeah.
Yeah, okay. Oh, there is a comment.
Yeah, I've read so if you like Google my name and Rosa, you will find a paper, and there's actually like all the other authors are the Rose experts. I just did the data analysis. So
I actually know your name.
yeah, we've met before. Yeah.
Yeah, I'm sometimes a bit. I would definitely pin you within polyploidy community. I think I might get lost on details, but
Yeah, no worries.
But I think we've interacted, right?
We've met in Cologne at a conference some years ago.
Yeah, of course, with Tony.
Yeah, I was talking about my diploid plant there, and it's annotated as an octoploid, which I thought was just hilarious. But yeah,
of course.
Typical mistake.
Good. I'm glad that the world is not getting too much bigger for me. That I'm bumping into the same people. It's easier for memory. Okay. Comment on situations where it seems like diploid should be deployed, but we see smudges coming up for triploid and tetraploid. I think that just boils down on giving you multiple hypotheses of what your genome can look like. One valid hypothesis is that this is a genome that has some local duplications that just expanded within the last few million years. And you just see lots of legacy of that. The other one is that there was some sort of whole genome duplication at some point in the past, but it already degenerated. And which of the two it is, it's not sort of possible to tell on the KML level. This KML level is efficient because it's super simple to compute. It's very efficient to compute, and it's a very raw way how to visualize your data. You can believe in what you're doing because of this. It's not doing any cheeky transformations you would behind the scenes. This is very much as pure as visualization as it can possibly be. But it hardly ever gives like a full answer. So I would just pay attention to the assembly. I would run genome scope with both options and get the explicit prediction of what you want to see. Just confront your genome with the genome scope. Use things like FastGA to then just take the genome and align it to itself. This will give you a different way how to look at the polyploidy of your genome. Because that's about it. Use Mercury as well. That's a really good tool. This is a tool that will give you the KML histogram and plotted it by the count number within the assembly, and it also helps you to sort of interpret of what are haplotypes and what are just Yeah, what are haplolines, what are haploid levels and duplications. Duplications tend to be always uncollapsed, or like as much uncollapsed as possible, while the heterozygous sizes tend to be collapsed. Yeah. Good.
Okay, I have an entirely selfish request. One of the smudge plots on your presentation is one of my study species. Can you go back to the Salix arbuscula plot?
Oh, I picked a bunch of ones from the GitHub, so it's possible. Which one?
It's the Salix arbuscula. So like sail or I don't know. You had it in the presentation that you had.
So is it a tree of life, or is it a?
I mean, it should be a tree of life one. It was arbuscula. It was one of the ones you showed towards the end.
Towards the end. So was it within the doc?
No, it wasn't in the doc. It was in the slideshow.
I might know that's one. No, oh, that's the yeast. This is unlabeled. That's the same one. Puka, no, Flagaria, nematode. What was the total ID again? Could you just Sal Arbu? I figured it was here. No? Where did I put it? I don't see it anywhere in my talk.
I thought it was in like the Google Slides you were sharing.
Does anybody remember seeing that? Nematodes, strawberry, wasps, strawberry. Nematode, strawberry, blah, blah. Automatic. Oh yeah, it is here.
Yes. Okay. I was very concerned that I was losing it for a second.
Yeah, so
It's beautiful.
I guess I did not really pay attention all that much because here I focus on the speckliness, not really on the all that much on the underlying bio. It also looks like almost that simple genome.
I mean, that is to be expected. I just wanted to look at it in more detail.
Yeah. So I would say this is so overwhelmingly dominated by the heterozygous sites that I would not be worried that this is really a polyploid. Right? I would just haploid levels of this individual smudges interpret as genomic structure. I would say if there's something funky going on, it's very well hidden.
I mean, that's it from me. Thank you.
By the way, the reason why it's hard to understand you is because it's somehow double echoed. Every I don't know why is that, but I'm glad that we actually managed. Okay, is that it? Final question. What version? That's a great question. So, that's one thing I did not do at all. I did not show you how to use the Pythonic version. Well, I would actually advise you against doing that. So, I would say don't use double hang. Please don't use double hang. You can use Oriel if you have very high coverage. It's a very stable version. It just does the job, and you might even have less troubles with the reviewers. But people don't really know versions of Smudgeplot, so but it's just this is well established. I guess the journal with that will most likely give you hell is New Phytologist. So, half of my citations are from there. So I would say if you have very high ploidy genome and you struggle with the sploidy plot inference because of the fishnet cutouts. So if it gives you like too much spread of smudges for different like strange ploidies, then you might want to downgrade to Oreo for now. But for majority of data sets, for those that are not insane coverage and not insane ploidy, ploidy plot is so much better. The inference is much more robust. The visualization is so much prettier that I would the only thing you're missing is the label proposed something. But the proposed something always was anyway just sum of all the rows and just which one is the max. It's a I I really would like to discourage people from not using not thinking about the inference when they're using the tool. I feel like it's misguiding people. It's creating an impression that this is the way how to do point prediction, and it's not. Maybe it will be one day when we will have these models well established and it will all make sense and it will be trustable estimate. But I think we're not at that stage yet. We are frontiers of understanding polyploid genomes. There were not that many people before doing that. So it means that we need to really know what we're doing. Yeah, that's about it. When I hope the new one will be out for this workshop. We're working on it. It annoys hell out of me, so I'm very motivated to finish it soon. Also, Jean is breathing on my neck too. I don't know. Soon. The problem is not about the amount of time we spend on it, but we're getting the breakthrough idea that will actually solve it. And I think right now we're all slowly converging on just creating explicit models. Just co-estimating heterozygosity, level of duplications employed at the same time, and we're thinking whether we can consider only duplications and that would be sufficient model, or if that would be too much of a problem, if we need to do some sort of distribution of copy numbers or things like that. Like it's a very non-trivial problem. I don't know how to emphasize the non-trivialness of that whole procedure. But the fun thing is that Richard Durbin and Chen Shi wrote this, and Jean Myers wrote this algorithm that self-aligns primary assembly. So you do assembly that just tries to separate everything as much as possible. And then you do full self-alignment and you look at the sizes of cliques with the idea that you will find cliques with the count that is mostly corresponding to ploidy. And it's actually very nice approach because it's very complementary to Smudgeplot. So every time Smudgeplot is wrong, they are right, and other way around, because Smudgeplot is very good with the recent polyploidization events, while they're good with the generated polyploidization events. But guess what? They actually don't have a good model for the sizes of those cliques. They have exactly the same problem. They say the highest one is the one that is myploidy. Although, obviously, if you have approximately the same number of tetraploid and diploid, it's clearly tetraploid. It cannot be diploid, right? So what I'm saying is that we actually do like this model. That model needs to happen. I don't know, man. Am I making sense? It's a okay. 25 minutes overtime. It's time to go. I'm glad you're having good times. I'm having good times too. Right. Bye all.
It's a lot. Bye.